Velocity is highest where along this channel? On the outside, correct? Okay, so if I'm drawing the arrows proportional to the velocity, the largest arrow, that is the highest velocity, is going to be on the outside, and the smallest arrow, the lowest velocity, is going to be on the inside. Again, point bar. And where erosion is occurring, we call the cut bank. So again, highest velocity on the outside of, excuse me, of the curve on the cut bank, lowest velocity on the inside. And then we get a transition so that the velocity is highest on the opposite side and velocity is lowest on the inside of the bend, and so on down the stream. What I have drawn here is a symmetrical cross-section. So if you were to draw a line between these two bends, like here, so we'll call this point A and this point A prime, this is approximately what this cross-section is going to look like. And I'll draw a fish. So, you know, it's a stream. If I, on the other hand, drew a cross-section, call this point B here, from A to B, what do you think this would look like?
Not symmetrical.
Asymmetrical. So how would the shape change? One part would probably be deeper than the other, correct? So which side is going to be the deeper side and which side is going to be the shallower side?
B is the deeper.
B would be deeper, A would be shallower. Excellent. So, okay, so you're going to get a cross-section, and again, the term we use in English is freehanding. This is not exact, I'm just sketching it on the board. So A to B looks like this. What we want to do is measure stream flow perpendicular to, we want to draw the transect, rather, the cross-section perpendicular to the direction of stream flow. So if you look at line AB, the flow is unevenly distributed across the cross-section. So we violate that assumption of measuring perpendicular to flow because in 3 dimensions you have these curvilinear vectors coming through. So what we attempt to do is to gauge along straight stretches. Sometimes in English we'll use the term reach. A reach is a segment of a stream. So we will try to gauge along a reach that is straight, not at a bend. And so when we do this, I'm going to get rid of my fish here. If you think, and I'm going to keep the math very simple here, your calculus I'm sure is much better than mine. Discharge Q is just dimensionally the volume, that is length cubed, divided by time. So this is the total flow. So this would be, for example, in liters per second. This equals, dimensionally, the velocity times the cross-sectional area. So velocity is in dimensions of length per time, cross-sectional area is dimensions of length squared. So if we were gauging in a ditch, for example, an artificial channel, say we're looking at an irrigation ditch that has a rectangular geometry, then as long as you know the dimensions, you know the depth, D, and you know the width, W, then all you have to do is measure the velocity coming through this plane, V. I'm drawing this should be normal coming out of the board. But because stream channels have irregular geometry, even though this scenario is simpler because it's at least symmetrical, how do you measure the cross-sectional area? What do? Do you know? You have to approximate it. Do you remember from integral calculus integration by parts? Have you heard that term where you divide up into segments? So that's what we are doing. We will take measurements of depth and of velocity at various points across the stream, and then we will add them up. So in effect, it is like integration by parts. So what we will do is stretch what we call a measuring tape, and I apologize, we're in America, so this is going to be in feet and decimal feet, like tenths of feet. Ultimately, we will convert the results to metric, to cubic meters per second or to liters per second, but because our measuring devices are calibrated or graduated in units of feet, that's what we will take our raw measurements in, our initial measurements. So we will measure velocity at this point. So 6, 7, 8, 9. I wish that it had been 10. I'll explain in a minute why I wanted this to be 10. Actually, you know what? Let me redraw this. There is a reason why. There's no eraser on that. There is a reason why the number 10 is kind of a standard number here. The idea is that you want no more than 10% of your flow through any one of these segments. Otherwise, the error gets large. You don't want, 1/3 of your flow to go through one segment, because if you make a mistake in that measurement, that will bias the rest of your numbers. Does that make sense? Mm-hmm. So let me try doing this in dividing it up into units of 10. And we will, and then I'm going to redraw this again. But let's say 1, 2, 3, 5, 6, 7, 9. Yes, all right, there we go. Good guess. All right, approximated 60% of the distance from the surface of the stream to the bed. So we don't take the depth halfway, we take the depth 60% down. That is right, John, isn't it? 6/10. So again, for shallow streams, for streams less than approximately 6 feet, 2 meters deep, the average velocity is at approximately 60% of the distance from the surface. And again, if you can't read my there are two issues here. One is I'm writing in English and you're used to Arabic or French. The second is my writing may not be clear. So if you don't understand what I have written, let me know. So 60% of the distance from the surface to the bed. So the term we use in English, have you heard this term before? The stream bed is the bottom of the stream. So this is the bed, and this is the bank, and this is the other bank. So the term bank just refers to the side of the stream. Cut bank is on the bend, and then the bar is like the bank on the opposite side where it is curving. But here, we'll just call this the bank. And this is the bank. Okay, so what I'm going to do then is measure velocity. So we'll call this point 1, or segment 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm going to measure V1, and then V2, and so forth across the stream, all the way to V10. So the way I divide this out then is I say Qn equals Vn An, where in this case n equals 1 to 10. I'm not doing this, I'm not using the right terminology. Qi equals VI AI. I equals 1 to n. In this case, n equals 10. So n is your number of segments. So this is what you can do for Q total. Total Q we will call QT, capital T. So QT is going to be V1 A1 plus V2 A2, and so forth, plus plus Vn An. So reasonably clear. I see Manal nodding. I want to make sure I'm not leaving people behind at this point. Sam, are you okay? Can you? All right. You guys good? Okay. Okay. So again, simple mathematics. I'm sure you remember seeing this at some point. We'll just do a summation series. You remember summation series?
Yes.
So you just say QT equals
summation of
I equals 1 to n, Vn An. So that's just this equation, short. Yes, thank you. Good. Yeah. It's early and I didn't sleep. Thank you. Okay. So we can break this down further. We said area for a rectangle, for example, A equals D times W. So we can break this out to say QI equals VI WI DI, where W is the width of each of these segments. D is the depth. And in fact, what we're going to do with the width is not the width of an individual segment, but rather the distance. Let me think of, no, I'm about to trip over this. This is correct, sorry. So W, I had it right the first time. This is width, this is depth. But the depth is actually going to be at the midpoint of each of these segments. So this is W, that's D. Sorry, I'm trying to talk and think at the same time. So what we will be doing here is saying QT equals I equals 1 to n VI WI DI. So in this case then, we will be measuring distances. Let me get a different color. Basically, I will have a measuring tape, a spool of tape that is marked in tenths of feet, hundredths of feet, and I will stretch the tape across the width of the stream, and I will note the distance from the bank to this point and then to this point, and so forth across the stream. And so what I will then get is knowing the midpoint between each of these two. No, I can measure. Each of these tiles is actually 1 foot. So if you look at the tiles underneath you, if you think, okay, my stream is 10 feet wide, so 1 foot, 2 foot, 3 foot, and so forth, then I would take a measurement. My first measurement might be at 1/2 foot, and 0.5 feet, and then 1.5 feet, and then 2.5 feet. So that's what we will be doing across the stream. We will be measuring, dividing it up into principal segment of how these measurements are made. If you look at the, I guess I sent him 2 different files. Disregard this last page that has only 1 sheet on it. You can use it to draw on whatever. If you look at the remaining pages, what you have here is an Excel spreadsheet. And so you'll see the columns: distance, depth, velocity. And then I had a lowercase, minuscule q. This should be a larger case, a capital Q. So what you would do is record these data in the field at each of these points, and then write them down in your field book, transfer them to the spreadsheet. And you can see on the back that I have printed out the same spreadsheet with the formulas. And the last column here that says %Q is a check on the error of, error is not the best way to put it. It's a check on the percentage of flow that is occurring through each cross-section. If you remember, I said, ideally you don't want more than 10% of your flow going through any one cross-section, any one segment of the stream. So this enables you to check what the percentage of flow is. And in fact, you can see that I had as much as 15% going through one segment. That's not ideal, but that's real life. That happens. So, yes ma'am?
I think this is more than 10 segments.
It is more than 10 segments. And so I'm going to explain why we do more than 10 segments.
Because when we explained, we told that 10%, we need 10%,
Right.
which is maybe representative.
Right. And so the reason I did 10 segments was that's kind of the minimum necessary. If every one of those segments has 10% of the flow, then that means that you don't violate your rule of no more than 10% being in each segment. Typically, what I do is I do more than 10 segments. I may do 20, or in this case, I don't know if that's 25 or 30. And I will just divide it up. I will measure at an even interval. So if you look at this column that says distance FIP, FIP means from initial point. So what I do is I will start at one end, and this bank, for example, say this is east, so north, south, east, west. I'm really in out of the way. So, say I'm gauging from west to east. My initial point will be the west bank, and then my final point will be the east bank. And so this will be my reference point. I'm pausing for a second to gather my thoughts, but also to see if there are any more questions to make sure that I'm not losing it. So, any more questions at this point? This will become clearer when we're in the field, I promise. We're going to stretch out the tape and we'll take the measurements. I'm going to draw this cross-section again and explain why what I showed originally is too simple. If you say, if we know that the discharge equals the velocity times the width times the depth, if you have segments that are each the same width, will the discharge be the same in all of those segments? No. Why?
So it depends on the velocity of the water in each segment.
Depends on the velocity of the water in each segment, but it also depends upon the depth too. So even if the velocity is identical, which it probably will not be, the velocity will probably be greatest in the center of the stream channel, correct? Velocity segments that are each the same width. Will the discharge be the same in all of those segments? No. Why?
So it depends on the velocity of the water in each segment.
Depends on the velocity of the water in each segment, but it also depends upon the depth too. So even if the velocity is identical, which it probably will not be, the velocity will probably be greatest in the center of the stream channel, correct? Velocity, but also the depth is greatest in the middle, correct? So if I have width constant, but either depth or velocity is changing, I'm not going to have the same value of Q in each of these segments. So that means by definition, if I have 10 segments and Q varies between the segments, I'm going to violate that rule, right? That some of the segments will have more than 10% of the flow because the velocity will be greater, the depth will be greater. So I can either attempt to estimate, okay, some of these segments are going to be narrower width, some are going to be wider, so I could do, this will be wider because it is shallow and the velocity is lower, and then as I get out, it's going to be narrower, and this one will be narrower still. You see what I'm doing? That I'm adjusting the width and the depth to make sure that Q1, Q2, Q3, Q1 equals Q2, which equals Q3. In practice, that's going to be difficult to do. I can adjust the width, but I can't predict absolutely how the velocity is going to be. So what I do is I do more segments than I need. Instead of doing 10 segments, I may do 20 or 30. And so if the stream is, for example, 20 feet wide, and I do a measurement each foot across, then that means I have at least 20 segments, correct? Or if the stream is 20 feet wide and I do a measurement every half foot, that means I have 40 segments. So that means that I will have enough measurements that I will not violate that rule about too much flow going through one segment of the cross-section. The trade-off is that every measurement may take a couple of minutes. And so you don't want to be out in the stream all day at one location. Usually we're doing multiple, we're gauging, I'll draw another stream like this. So we may be gauging here, and here, and here. I don't want to spend all day taking measurements at one point. So it's kind of an art figuring out how many measurements are enough without doing too many and wasting your time. Does that make sense? So my usual rule of thumb is I will start out, if it's close to the bank and it looks relatively stagnant, for example, you can see a stick or a leaf floating in the water. If it's not moving, that means the velocity is going to be relatively low. The velocity may even be unmeasured, maybe almost zero. So what that means is that close to the bank, I will probably start out with a wide measurement, maybe 2 feet. And then as I get farther out into the stream and the velocity increases and the depth increases, I may reduce my measurement interval. So when I'm out in the stream, I will be calling out, usually what happens is one person is taking the measurements and somebody else is recording the measurements. The instrument that I have, you can actually record it because it's digital. You can program it to record numbers. I don't trust that. I would rather write the numbers down so I have a physical record of my measurements. So what I will do if I am the person waiting, and I will demonstrate this first when we are in the field, and then other people will have the opportunity to do this, is distance, depth, and velocity. So I'll say, for example, I'm starting at the west bank. Let's say this is west. So I say, west bank. My first measurement is at 2 feet. Depth is 0.20 feet. Velocity is 0.01 feet per second. So then I will say, next measurement, I will go to 3 feet. Distance is, so that's your distance. Depth is, velocity is, and you will just record distance, depth, velocity at these various points across the stream. Yes, ma'am?
How do you measure the velocity?
So we have in the bus, and James also has, velocity meter, and there are different types. The one that I brought is commonly used. It operates by electromagnetic induction, so it is actually a sealed sensor, and as the water flows around it, it has been calibrated so that it automatically records the velocity. It has to be oriented in the proper direction. It has to be oriented, pointed upstream, so you have to know which direction the flow is coming from. Upstream. So let's say flow is, again, you can see a leaf or a stick floating in the water and detect which way the flow is going. But let's say flow is going from upstream to downstream. So you want to position yourself so that you are downstream of the tape, and you are taking your measurements with this instrument going upstream. Now, the instrument is connected to something called top setting rods. A rod is just kind of like a stick. It's a long, round piece of metal. These rods are calibrated in units of tenths of a foot. So you can look at the rod as you place it in the stream and measure the depth of the stream. So looking at the rod gives you the depth, reading the meter gives you the velocity, and looking at the tape across the stream gives you the distance. One other thing, because velocity is at 60% of the distance from the surface to the bed, you want to position the sensor at that point, and that point is going to vary with depth, of course. If I measured the velocity at the same depth all the way across, I wouldn't get the average velocity at each location. These top setting rods, again, we'll show you when we get to the field, are fabricated so that once you read the depth off the rod, there is a second rod. That's why we say top setting rods, plural, rather than rod, singular. There's a second rod that has a separate gauge on it, and you can manually adjust it so that knowing the depth of the stream, you then set the depth on the second gauge, and that has automatically positioned proportionally the sensor at 60% of the distance. So you can imagine these are pretty sophisticated. The rods cost $500, the meter costs $3,000. The meter is worth more than my car. So it's pretty rugged equipment. I mean, it can be broken. I hope we don't break it, but I have used this multiple times. But it's not, there are cheap alternatives. They're not accurate. So you want to use a meter with top setting rods. James has borrowed from the local office of the U.S. Geological Survey extra sets of top setting rods, but with a different meter. The meter that the survey uses is an older version, but it is their preferred version. And what happens is, do you know what an anemometer is? You know, that measures wind speed. You see little cups and it'll go around. If this is the rod, and it'll do like this. Basically, it's like an anemometer. It's called a the vein, what, you remember? I can't remember. Anyway, you wear headphones, and every time the vein goes around, the cup goes around, it makes a clicking sound. And so you learn to count the number of clicks, and the number of clicks is proportional to the velocity. I much prefer just to look at a readout and write down the velocity than counting the number of clicks. But again, this is a standard instrument. It's one that's used by the U.S. Geological Survey. I've never used one before. I've seen them, so this will be new for me today too. But we have several sets. We have my set plus one or two from the U.S. Geological Survey. So hopefully everybody will get the chance to, or as many people as want to, will get the chance to actually get out in the stream and practice. Now I realize that not all of you have shoes that you want to get wet, and that's okay. So you may want to work in pairs, where someone is out in the stream and somebody else is taking the measurements. But what I think we will do, we're going to go to several different locations along a short stretch, short reach of stream, is I will take a measurement with my meter, and then we'll see if you can repeat it. How much does it vary, what you're measuring from what I got in terms of the raw numbers. And then at the end of the day, or maybe when you get back to Athens, what we'll do is you guys will put the numbers you recorded into the spreadsheet and then calculate total discharge. Now, once you have calculated total discharge, so say this is point, I'll use a Roman numeral, call this point 1, call this point 2, call this point 3. One of the things about gauging at various points down the stream is you can look at, here's Q1, here's Q2, here's Q3. You can look at delta Q. So let's say in this instance, delta Q equals Q2 minus Q1. Have you heard the term base flow before? Do you know what base flow is? So base flow is the portion of stream flow that comes from groundwater, correct? There are two sources of stream flow. One is naturally anyway, if you're not talking about humans adding water to the stream. One is runoff after rainfall. The other is base flow, which is groundwater discharge. On a day like today, when we were gauging, and it has not rained recently, we should not have any runoff contributing to stream flow, correct? So if Q2 is greater than Q1, what explains delta Q? What explains the increase in discharge from this point to this point?
Additional flow.
Base flow, groundwater coming in. So you can use stream gauging at various points along the stream to measure base flow. Or, if there is a tributary stream coming in here, then the difference between flow at Q2 and Q1 equals the flow of the tributary stream plus whatever the base flow is. So you may want to gauge here and here so that you get base flow rather than having stream flow being part of the equation. Does that make sense? So if you want to measure only groundwater inflow, you have to measure along a segment of the stream where there is no surface water coming in. And you want to do it on a dry day when there is no runoff, when there hasn't been rainfall recently. Obviously, runoff is not instantaneous. So my usual rule is if there have been more than like 2 centimeters of rainfall, about an inch, I will wait 24 hours before I go out. I'm assuming that all of the runoff has subsided after about 24 hours. I use the term inch. One of the conversions that I did not talk about yesterday is in the English system as opposed to the metric system. And you can actually see this on this. No, this is all metric. Never mind. In the English system, 1 foot equals 12 inches. Why was it divided in units of 12 instead of units of 10? I don't have a clue. But historically, that's the way it is. In fact, I think in the back of your book, you probably have a scale that shows it in inches, like inside the back. cover perhaps. Right, it's, the conversion is in there, but also if you look at, I'm thinking on the page itself, that's metric, that's, I guess it's not written in, the conversion is written in the book, but the scale is not itself in the book. You don't have you don't see the ruler inside the book, but the conversion is in there. So anyway, what I will be trying to do is giving you distances in feet or fractions of a foot, decimal feet, but I may screw up occasionally and give you a distance in feet and inches. So for example, if I say 1 foot 6 inches, that equals 1.5 feet. But because it's in units of 12, and I have to do the math in my head, you know, what's 1 foot 1 inch? Well, it's 1 foot and 1/12, so, you know, what does that work out to? 1.08 or something like that, I don't remember. Anyway, because the stream, 0.8333, I think that's right. I will try and do the conversions in my head, but it may be that the tape measure that I'm using is not graduated in decimal feet, it may be in feet and inches. And so I may just call out to you, West Bank is at, you know, 1 foot 7 inches or something like that. Again, I realize this may not be clear, hopefully when we're in the field.
Maybe we use feet and at least we make conversion.
Yeah, I mean, you could do, it's, I guess my philosophy is the less conversion you have to do, the less error potentially gets introduced. So, you know the conversions, but you know, every time you do a calculation, there's the possibility of making a mistake. And so, you know, the more calculations, the more mistakes can happen. What usually happens with the bank is that I'm not able to anchor the tape exactly on either end of the bank. That, you know, it may look like this, and if the stream, here it is. So if the stream is here, I may have to stretch my tape measure from here to here because I don't want the tape dragging in the water. So what I'll typically do is take a stake or a screwdriver or something like that and anchor it on either bank. But what that means is that I have to know the distance from this endpoint to the stream, and then the distance from this endpoint to the stream. So that's why I was saying when I'm dealing with fractional distances or distances in feet and some number of inches, it may be because I'm calling out the reference, the distance from the reference point to the edge of the stream. Whew. I've been talking for 45 minutes. Yes, ma'am?
For the deeper streams, we use pumps.
Ah, yes. Excellent question. In fact, I don't know whether James shut this down or not. John, do you know?
You just let it try to alarm on. You said it takes a long time.
Okay. Let's open now. Oh. It's password protected. What a pain in the butt. Okay. Remind me, next time we're in the classroom, or if James comes in and I can fire up get the login information, there is a site that is operated by a river basin management agency in the eastern United States that talks about different types of stream gauges. And for deeper streams, you're right, we have to use a boat, or we have to go on a bridge and walk across the bridge or something like that. And some places there may be what's called a cableway, where you've got, you know, like at ski resorts where you take on the y-axis, depth will be your independent variable on the x-axis. And so you've measured the discharge at various individual points to calculate the total discharge, QT. So, I mean, we can call this if you want QT. This is the discharge at a cross-section, across the entire width of the stream. And the depth here is going to be, you know, relative to some data. So you're going to have a reference point on the edge of the stream. So the idea is that you do this gauging under a variety of different conditions. Variety of stream depths. You do it after a storm. I said when you're calculating base flow, you don't want to have any runoff. But under other circumstances, you would want to know the discharge after storms of various magnitudes. And so you go out, some little gauging site. And so you wind up with this rating curve, which is an empirical relationship between stage and discharge. Stage is another way of saying depth. So if depth is this, if depth refers to how far down the stream is below the surface, stage refers to the height of the stream above the datum. So that's just another way of saying depth. So stage equals stream height above datum. So when we say flood stage, that's when the stream is beyond bank full. So at flood stage, the stream is out on the floodplain, correct? It's out of the channel. So that's another instance in which the term stage is used. Do you think, well, I have already said that this empirical relationship is unique for each location. And you can't predict it arbitrarily. You think it's not unique?
Not unique for other location and not unique for the same location.
Right. I think you're saying what I'm trying to say, but phrasing it a little bit differently. What I mean is that every location has a different relationship. What you're saying also is that it could vary at a particular location. So what are the circumstances? We have gauged at low flow, at high flow. So we've developed this relationship for, say, this location here. Why would we need a new relationship? Why would we need to recalculate that periodically?
Because the conditions may vary.
Exactly.
So the river can change after the storm.
Yeah, you can have erosion, you can have deposition. Now, the idea is we assume that it's not going to change very often. So these rating curves may be recalculated every few years. But if you think of development in the watershed, if you're changing land use or land cover, if you have more what we call impervious cover, if you have more paved surfaces, more houses, runoff is going to change, correct? So that in turn will change the rating curve. So if a dam is constructed upstream, that's obviously going to affect flow also. So the rating curve will need to be recalculated every so often, every few years perhaps, but certainly after major changes in the watershed, such as development. Again, I assume that some of this is familiar, but maybe not every detail. I know that not everyone has the same background in this group, but hopefully the concepts are understandable. So, do you have any questions at this point? Is there anybody? Yes, ma'am.
The V on the x-axis. It's the distance.
I'm sorry. That's depth. I've been using D as depth previously.
Depth.
Depth. D. Depth. Or stage height. Either one. It's just a measurement of. It's the reference of the vertical position of the stream at relative to the discharge. What's that?
At what point?
Well, that's what I'm saying. It's you pick an arbitrary point. So I will put like you're surveying for elevation. You may put a survey marker down and say, this is my datum. And my datum is on the bank right here. and I have a staff gauge. What are my data? Think of Vicksburg again. The data may be the flood wall, the top of the flood wall. That may be your reference point. And so you're measuring either the depth of the stream or the height above the reference point.
At different times.
At different times, correct. Obviously, you want it, this is perhaps not, how can I say this? This relationship doesn't work if your reference point is not underwater, correct? You have to have the reference point underwater, so your datum is going to be at some point in the stream. But presumably, you're going to have some kind of measurement, you know, some very long meter stick or something like that, that will enable you to figure out what the height is. Staff gauge, that's the term I'm looking for. This thing is called a staff gauge. Boy, I really am. So the staff gauge is your graduated reference point that shows the height. We didn't see that on the flood wall in Vicksburg, but oftentimes on flood walls you will see staff gauges. John, I'm thinking the Delaware River Basin Commission.
Okay.
It's like drbc.org or something like that. That's a staff gauge. Excellent. Thank you, John. So that's what they look like. So you can see it's graduated in units of fractional feet. So you have this sitting on the side of the stream.
Okay, Delaware Basin.
Yeah, Delaware River Basin Commission. So drbc.org, I think. Yeah, there we go. And then if you, there should be a link in here about stream gauging. No, I don't see that. Can you do a quick search up there and do stream gauges in their search term? Or just stream gauge. Oh, come on. Keep going. Go to the next page. That's frustrating. Importance of stream gauges. Thank you. That's it. It spells gauge with a G. You will see gauges spelled two different ways: G-A-U-G-E or G-A-G-E. I'll even sometimes spell it two different ways. Okay, so yeah, here we go. The importance of stream gauges. Thank you, thank you, thank you. All right, so brief history of stream gauges. There are pictures of different types of stream gauges. If you go down to, how are data, if you go up to the link up top, John, that says, how are data collected and transmitted? I think that's it. Link number 4. Yeah, there we go. So what you can see here is, typically for large rivers, there will be something called a stilling well or a gauge house, because you want to minimize water level fluctuations in your measuring point. And so your staff gauge is going to be off to the side of the stream, and there will be what's called an automatic water level recorder. So it will measure the depth of water in the stream. And then that in turn is what gets converted to discharge using the rate. So this automatic water level recorder is sometimes, now it's usually electronic. Usually there's a pressure transducer that's connected to a digital data logger. And it's actually, you see satellite or radio transmitter up the top. It's automatically uplink. So the numbers are recorded and transmitted automatically. So if you go to one of the other ones, open ones here, yeah. Let's do, on the U.S. Geological Survey's Water Resources Division website, usgs.gov. If you look at this map here, today's water conditions and current stream flow, this is a map of real-time stream flow compared to historical data in the United States. Each of these colored dots represents a stream gauge. We're out here. I will click on this in a minute. But what is happening is that these data are being collected in real time, that the stream depth or height, the stage, is being monitored in real time, and then automatically being converted to discharge. And so this is a map of the 50 states and Puerto Rico and the Virgin Islands. So let's click on Texas. Actually, before I do that, let me show you. These numbers don't represent absolute values of discharge. For example, in cubic feet per second. The unit of discharge you'll often see is cubic feet per second. Instead, these represent relative values compared to the historical record at each site. So a value that is from 25% to 75% of the long-term average has a green dot. A value that is really low is red. A value that is really high is blue or black. So you can look at this map, I'm going to steal that meter stick, and see places that may not be in drought yet, but at least are relatively dry. And here's Kentucky, here's Indiana, here's Illinois. River, Vicksburg is right there. The Missouri River comes in like this. The Ohio comes in like this. So in the Ohio River Basin, we're having below normal stream flow right now. That may not mean we're in a drought. It just means relative to this time of year, historically, flow is lower than normal. If you look in some parts of the eastern United States, particularly Florida, you can see some places where stream flow is much higher than normal, others where stream flow is much lower than normal. Generally speaking, most of these dots are green, right? So stream flow is generally normal across the United States. So let's go to Texas. You click on the map of Texas, and then see if we can find San Angelo. Tom Green County is easy to pick out. That's the funny color in there. Concho River, San Angelo, Texas. That's where we are. So, John, can you go ahead and click on that, and that should bring up a link to the hydrograph. Ah, I love this. So, this is the summary. The area of the drainage basin upstream of the gauge. The discharge, CFS, is cubic feet per second. So, again, it's an English unit. Stage, 1.65 feet. Again, it's relative to a local data. Flood stage is 26 feet above that data. So obviously, it's not flooding right now. Okay, so if you click on the hydrograph, and I don't know whether you can zoom that. Oh, fantastic. Okay, so every single gauge that the United States Geological Survey is responsible for, and there are like 7,000 of them, will have these data on the web. It's a wonderful tool. So what you see here is discharge plotted in cubic feet per second, and this is a logarithmic scale over time for the last 8 days. So yesterday back to June 8th. So this is basically a 1-week period. And it rained earlier in the week. You can see hydrograph recession, flow was dropping off. Again, note this is a logarithmic scale. And then response to rainfall. And then it dropped off, and then it rained some more, and then it continued to drop way off, and then it went way back up again. So it's possible, I'm just guessing that this was a rainfall response. This could have been a reservoir release. They could have let water out from behind a barrage, a dam, upstream, and it peaked. There are various reasons why hydrographs respond this way. In western United States, hydrographs will respond to snow melt. So you will see, you can look at a hydrograph over various periods of time. What you typically see when you go to the U.S. Geological Survey's website is just as a default value, the last 7 days. But you can actually go in and calculate for any historical period of record. And so you can look at an annual hydrograph as opposed to a seasonal hydrograph. And that way you can see how the flow responds, an annual hydrograph as opposed to a weekly hydrograph. And that way you can look at how flow responds seasonally to snow melt, to drought, to if you've got a wet season, that kind of thing. So I'm going farther than I anticipated in terms of the things that I am discussing this morning. But I guess what I wanted to do was talk about how, once you make these measurements of discharge, how they're used. And if you look here, this is what's called the stage hydrograph. This is actually the raw data showing the height that's being, or the depth that's being measured at the gauge. John, can you scroll back up?
Yep.
So that in turn is automatically converted to discharge using the rating curve. And if you look at the two curves, you know, they pretty much look like each other, right? But it's not necessarily a linear relationship. In fact, it's probably a non-linear relationship, just the way I've plotted it. Oh man, so anyway, we could spend a lot more time, and in fact, Adam may be spending more time once you guys get back exploring the data available on the U.S. Geological Survey's website. So they're the professionals, they're the pros. They do this routinely. I do it for research purposes, I do it for teaching purposes to show students how these measurements are made. Yeah, so is that the rating curve? Oh, fantastic. That's really cool. Yeah, so it's a nonlinear rating curve. And this is a log curve. They've upgraded the website recently, so there's all kinds of stuff that's available now that didn't used to be available. Have you seen this, James? Customized rating curve builder?
No, sure.
This is for the Concho site.
How cool.
Yeah, so every single gauge site in America, particularly where they have these data, you can build your rating.
Now, which Concho site? 'Cause
I think this is downtown.
Okay, because what happened was they used to have about 10.
All right, they discontinued some of them.
They lost them, right? They tried to get us to take them over, but we didn't have the money to.
Unfortunately, the U.S. Geological Survey depends in part for its money on other users, that it gets some money from the federal government, but I think for the Water Resources Division, it's like 20% of their money comes from annual appropriations and 80% comes from contracts and grants. So there are other agencies. John, if you go back to the home page for the gauge, which may be here actually, just scroll up. Oh, actually you're on the state one. So go back to the, click on the dot, the green dot for the Concho.
This one?
Yeah, go ahead and click, it may be hot link through the blue, through the gauge number. Oh man, no, what I was,
There.
yeah, bingo, that's it. So if you look at this, if you keep scrolling down, yeah, I saw it earlier. Anyway, there was information that showed that there were other agencies that were helping with the United States Geological Survey. Basically, the Texas Water Development Board is giving money to the United States Geological Survey to help pay for this. Why? You know, it's not just scientific interest. It's because they need to know how much water is available for irrigation. They need to know, yeah, there we go. So City of San Angelo and the Texas Water Development Board are paying the USGS to collect these data because they use the water in the river. They want to know how much water is going to be available as a resource, but they want to know about flood hazards, for example.
Right. That's too cool.
Yeah. So I'm beating the dead horse at this point, I think. Let's get out and start